Okay, the last section in this chapter is on the meter bridge, and the meter bridge is an extension of the Wheatstone bridge. So it's related to the Wheatstone bridge. So let's have a recap on that first. If we have 4 resistors, R1 and R2 are in series, R3 and R4 are in series, but they're each in parallel sections. Then if it's balanced, that means if a current doesn't flow through that middle section which hasn't been included there, R1 over R2 will equal R3 over R4. What a meter bridge does is it takes out R3 and R4 and replaces them both with a meter of wire. Something like this. And there's that galvanometer in the middle section. So R3 and R4 have been replaced with a length of wire L1 and a length of wire L2 respectively. Now, if you look at the galvanometer, you'll see below the galvanometer, which is the thing with the circle and the arrow upwards, and a galvanometer is a microammeter that can tell you whether current is flowing one way or the other. On the bottom of that, there's a squiggly line connected with an arrow on it. That arrow is a metal contact, and you can slide that metal contact left to make L1 smaller and L2 larger, or right to make L1 larger and L2 smaller. And what you do is you'd set this up and you'd slide the contact left and right to adjust L1 and L2 respectively until the galvanometer reads 0. When that's the case, we know the bridge is balanced and R1 over R2 equals R3 over R4. Obviously here we don't know the resistance of the length L1 or L2, but what we do know is the resistivity formula can be rearranged to give us R multiplied by resistivity by the length over A. That means that R3 is equal to the resistivity of the metal by L1 over the cross-sectional area of the wire, and R4 can be given by the resistivity of the metal by L2 over the cross-sectional area of the metal. Now, resistivity and cross-sectional area will be the same for both L1 and L2, so when you put R3 over R4, the rows and the A's will cancel, and your formula simply becomes R1 over R2 is L1 over L2 when the bridge is balanced. Now let's see how it'll work. In this instance, a meter bridge is going to be used to determine the value of an unknown resistor. So to do that, you need the value of a known resistor. That's going to be our R1. You slide the contact, which is where the arrow is, slide the contact on the green meter length of wire until the bridge is balanced, and then you'd measure L1 and L2. So here we go. So we know one resistor, we don't know what R2 is equal to. We slide the contact, which is where the arrow is, along the green line until the bridge is balanced, and we get 40 centimeters on the left of that arrow and 60 centimeters on the right. Obviously, this is not to scale. So our formula is R1 over R2, 4 over R2, is equal to 40 over 60. Solve for R2, we get 6 ohms. Okay, second example. In this instance, you're only given one length. Now, if it's a meter wire, it makes sense that the other length is 80 centimeters. So to calculate the value of the unknown resistor, it'd be 10 over R2 is equal to 20 over 80. Solve for R2, 40 ohms. The third example is something that comes up in the Leaving Cert and is not really applicable to real life, because the purpose of a meter bridge is to get a value for an unknown resistance. So let's have a look at this. So in this case, we're given 2 resistors, a 10 ohm and a 40 ohm. We're told that L1 is equal to X. We don't know what L2 is, but it would make sense to say that it's 1 meter minus X, so it's 1 minus X, and we're looking for a value of X. So if you put into the formula, 10 over 40 is equal to X over 1 minus X, and you should be able to cross multiply and solve for X. I'll ask you guys to do that now and post your video on the Edmodo page. Alright, just to finish this off, uses of a meter bridge. It can determine the resistance of an unknown resistor. It's more practical than a Wheatstone bridge because you only need one known resistor to find the value of one unknown resistor, and then you just need a meter of wire. Second point is how it works. You slide the contact along the meter of wire until no reading is displayed on the galvanometer, so the bridge is balanced. And then, very important, this is also a null method. So there either is not a current flowing or there is a current flowing. There's no in between. If there's no current flowing, the bridge is balanced, the formula applies. If there's a current flowing, the formula doesn't apply. So you can definitely get a value for the resistor, but there's no error associated with that measurement of the resistance. So that's an advantage of using a meter bridge as a means to measure resistance. It's a null method. A disadvantage then, look, just for completion's sake, is that it's tedious to set up. And it's not as straightforward as using a digital multimeter set to read resistance.